Normally, we host this free seminar series on a bi-monthly basis as a way to highlight the cutting-edge research being led by our consortium members. With the spread of COVID-19 throughout the world, we have moved up this webinar as a way to keep the transportation discussion going as we adjust to this new normal. We are also excited to announce our 2020 this year Global Symposium on Connected Automated Transportation is moving online and is entirely free. We have condensed our program to fit in a one-day event with 30 speakers confirmed. Registration is live now at ccat.eventbrite.com. Today's research review is presented by Drs. Yiheng Feng and Shuo Feng of the University of Michigan. Dr. Yiheng Feng is Assistant Research Scientist at University of Michigan's Transportation Research Institute. He received his PhD from the Department of Systems and Industrial Engineering at the University of Arizona in 2015. His research focuses on smart transportation systems, including traffic control with connected automated vehicles, cybersecurity of transportation infrastructure, and connected automated vehicle testing and evaluation. His research articles has appeared in several major transportation journals, including Transportation Research Part B, Part C, IEEE Transaction on ITS, and top security conferences such as NDSS. Dr. Shuo Feng is currently a postdoc researcher in the Department of Civil and Environmental Engineering at the University of Michigan Ann Arbor. He received his bachelor's and PhD degree from the Department of Automation in Tsinghua University of China in 2014 and 2019, respectively. He was also a visiting PhD student in the Civil and Environmental Engineering Department of the University of Michigan from 2017 to 2019. His current research interests include testing, evaluation, and optimization of the connected automated vehicle system. Please go to Mcity.com, which is MENTI.com, and enter the code 992382. Ask your questions. Be sure to mute your microphone for the duration of this presentation. And without further ado, let's begin. Dr. Feng?
Thank you, Harry. Today, Shuo and I are going to talk about this recent research we have conducted. It's related to the safety assessment of highly automated driving systems. So about the acronym, people have different acronyms about this automated driving systems. Some people call it connected and automated vehicles. Other people sometimes call it autonomous and connected systems. And broadly, we refer to the SAE level 3 or high vehicles. So that's our target. And this is what this research is focusing on. So this presentation will be jointly presented by Shuo and me. I will start the first half, and then Shuo will continue to present the second half. So, okay. So first, let's talk about why this is an important problem. Because so far, the different ADS system has been tested on public road, and a lot of statistics shows that they're not safe yet. Right? These two figures show two representative crashes involving the autonomous driving functions. First one is the 2016 Tesla crash, and the right one is the 2018 Uber crash, and actually in both of them people died in these crashes. And if you check the California Department of Motor Vehicles website, and you will find a much longer list of the crashes or vehicle collision reports related to the autonomous driving functions. And if you simply compare the performance of the current ADS versus the human drivers in terms of miles per crash, and you will find that actually the current level of ADS is much worse than the average human drivers. So this becomes a very important to assess the safety performance of the ADS. And this is also a multidisciplinary research, of course, because we are testing vehicles, so it is an automotive engineering problem. And because of all the sensors equipped on the ADS, it's also an electrical engineering problem. And with all the software and hardware, it's also a computer science and engineering problem. With all that, it is also a transportation engineering problem. Because if you want to test the vehicles on the road, you need to put the vehicles to interact with the multimodal traffic in a multimodal traffic flow, right? And if you can see this picture, this ADS, this vehicle is interacting with all kinds of road users. So that makes it also a transportation engineering problem, and that's also the angle we want to tackle this problem. So there were mainly three existing safety assessment methods. One is simulation, the second is closed test facility, and third one is the road test. They all have pros and cons. For example, simulation is very cost effective, but it's been proved it's very difficult to actually really model the vehicle dynamics in simulation. Then the road test, the public road test, is the most realistic one because it tests the real vehicles in a realistic traffic environment. However, as I mentioned in previous slide, the public safety is still an important issue. Accidents or even fatal accidents happens still with ADS. And another limitation or the problem with the public road test is it requires billions of or even trillions of miles of road tests to collect statistical significant results, because the on-road test is very inefficient. So test facility as an intermediate step between the simulation and the road test have its own advantages. For example, it tests the real ADS, right? So we don't need to model the vehicle dynamics in simulation, and the test facility provides a controlled and safe environment so that we don't have public safety issues. And also in test facility, we can design and repeat those interesting testing scenarios again and again to increase the test efficiency. So these are the advantages of the test facility. However, there's also limitations associated with test facility. One limitation is that it's empty. It does not have background vehicles. You can see the two figures represent the Mcity Test Facility at the University of Michigan. You can see that we built a very fancy and full fidelity test facility with different kind of road geometry and also infrastructures. However, it's empty. But if you want to test the performance of the CAE, it needs to interact with other traffic. This is one limitation. And the second limitation is different from the public road test. Testing scenarios in test facilities, as well as in simulation, that's the same, need to be designed purposely. So if you deploy the vehicle on public road, basically you do not design the scenarios, right? You let the vehicle to encounter the scenarios naturally. But in a test facility or simulation, you need to design the scenarios. So how to design the scenario to make an efficient test or evaluation, that becomes an even bigger challenge. So to address these two problems, we designed this new assessment framework to tackle these two problems with two pillars. So to solve the first problem, we developed this augmented reality testing environment in which we generate a virtual test facility in simulation, as shown on the left figure, right? We generated a simulated Mcity which replicates the road network and infrastructure of the real Mcity. So those simulated so we run the simulation, the simulated Mcity in real time, and those simulated vehicles will broadcast their vehicle information in real time through the roadside units installed in the real facility and then to the testing vehicles. So that means when the testing vehicle is running on empty roads in Mcity, but it can see or hear those virtual vehicles, so it can interact with those simulated vehicles. And at the same time, the testing CAV will also broadcast its own information through the RCUs back to simulation, so that the virtual vehicles can also see the real vehicle and its behavior, so that the virtual vehicle can also interact with the real vehicle. So that interactions are two ways, right? So, and also the infrastructure information, like the traffic signals, are also synchronized between the two worlds. So different type of vehicles can react to the same signal indication. This is the main concept. So in order to build such a platform, we need first a test facility. We use Mcity, right? And we need a test vehicle. And we use Mcity's Lincoln MKZ vehicle, which is a level 4 ADS. And you can see the bottom left figure, we installed the different sensors and communication system to the vehicle. And also we use the DSRC as the communication system between the real world and the virtual world. And we use Vissim as the simulation platform. And finally, we developed a data collection and management system to analyze the results. So this video is a demo of the augmented reality environment. So you can see on the left-hand side, this is the virtual world. And so you can see all those blue vehicles are the simulated vehicles, and the yellow vehicle is the real vehicles representation in the virtual world. And on the right hand side, this is the real world. You can see this is the vehicle's view, and the vehicle is driving on empty roads, but all those blocks on the bottom right figure shows those virtual vehicles from the real vehicle's point of view. And in this particular case, this real vehicle wants to make a left turn, but it has to wait for the upcoming through vehicles. In this case, we simulated a virtual red light running vehicle, and this vehicle runs the red light. So the real vehicle actually has the right of way, but it detects a potential collision, so it stops. So this is kind of the scenarios. It's very rare in the real world, right? Even if this vehicle passed through 1,000 sections, it may get one red light running vehicle. And another benefit of this is that during the testing stage, the crash is inevitable. But in this system, even a crash happens, it's going to be between a real vehicle and the virtual vehicle. So there will be no real damage to the real vehicle. So besides vehicles, we can also simulate different other modes of traffic, right? In this case, we simulate a high-speed train and to interact with the real vehicle. And so the train is also equipped with this communication system to send its real-time information to the real vehicle so it can interact. So for the details of the video, you can watch our YouTube channel. Due to the time, I will just continue to our second problem. So this augmented reality testing platform basically is only a platform, as I say, to generate the background traffic to interact with, or to generate the testing scenarios to interact with the real testing CVs. But the more important question is, how to generate those testing scenarios systematically? So this is, we call this testing scenario library generation problem. So first, we need to we want to make clear that because the number of scenarios is too many, so enumeration of all scenarios is impossible. For example, this is the scenario definition from the Paxos project, and they defined the testing scenarios in a hierarchical structure. So the first level is scenario category. That means different types of vehicle maneuvers, right? Like cutting, free flow driving, or following, or lane changing. And then the second level is the environmental level, which means what is the weather condition, speed limit, and lane number. And we call this static elements, because usually they're not changed during the execution of a scenario. And then on the lower level, we call this specific scenario or specific level. That means that represents different maneuvers of the background vehicle. So for example, the background vehicle can have different initial speed and position, different, take this cutting case as example, they can have different position speed, cutting position speed, and also the cutting angle. So even if the first two levels are given, with all the combinations on the specific level, it will generate hundreds or even thousands of scenarios. Not mentioning if we combine all the three levels together, if we multiply them together, the number of scenarios is almost infinity. So that means the enumeration of all scenarios is impossible. And the second, the basic assumption is that the importance of different scenarios are different. If every scenarios are equally important, then we have no choice but to test all the scenarios. Only if a small number of critical scenarios make the major contribution of the testing and evaluation, then by only testing those small number of critical scenarios, we can make a comprehensive evaluation of the overall performance. And we call this the small number of critical scenarios as our scenario library, and the process to find those critical scenarios, we call this the scenario library generation problem. Okay, so before talk about the detailed problem, let's take a look at our baseline, which is the public road test. That means if we directly deploy the vehicles on the road. So if we want to assess the safety performance of the vehicle, so one prevailing performance index we use is the crash rate. So we define here as the big A. The A is defined as the event of interest. Here it's crash. It's an accident, right? So then the P of A basically represents the crash rate of that vehicle, of this vehicle. And then the decision variables X here means the dynamic elements on the road, and the decision variable theta here means the static elements, or we call this our operational design domain, ODD, during the scenario. So if we map this back to the figure, so thetas are the scenario categories and environment parameters. We assume they do not change. At this current stage, we assume they do not change among different scenarios. And the axis are the parameters at this specific level for different scenarios. Basically, that means different realizations of the x. The x can be a vector of variables. Okay, so and then this px means what is the probability this x happens in the real world, right? And this pa given x means given the scenario, what is the probability of the crash, right? And if we sum of them together, that becomes the crash rate. Okay, and if we sample from the distribution of the px based on the Monte Carlo theory, right? If we sample n times and m times there's an accident happen, then the accident rate can be simply estimated by m divided by n. However, the problem is that because A is a real event, right? Because accident is a real event, so we need to sample a very large n to get an accurate estimation. And that is exactly why the public road test is very inefficient. We need to test billions or even trillions of miles to get accurate estimation. However, if we can construct a new sampling distribution, so notice that previously we directly sampled from the px, but if we can construct a new sampling distribution, let's say qx, and if this qx fulfill the following condition, then basically if we start to sample from qx, we can get same estimation. And from the statistics, this is called the importance sampling, and this qx is called a importance function. Right, so if we sample from qx, then we can get a new estimator p hat. And then the number of the minimum number of required tests depends on the estimation variance sigma. And of course, it needs to we need to predefine the precision level first. For example, if we use the relative half weight beta as our precision level and alpha as our confidence level. So when alpha and the beta determine, then the number of minimum required tests is related to the variance. The higher variance, the estimation variance, we need more number of tests. So now the question, the research question becomes how to construct the importance function qx so that first this new estimator p hat is an unbiased estimator. And second is the number of required tests is smaller than the public road test, or the testing miles is fewer. So then the first, the question means the accuracy of the proposed method, and the second means the efficiency of the proposed method. So to construct this new sampling function qx, so the first question we need to ask is what scenarios are important, or what scenarios are more critical. So we think that scenarios that are more challenging and difficult or more dangerous for an ADS, and also the scenarios that are more common in the real world are more important. So based on these two criteria, we define the scenario criticality V as the combination of the maneuver challenge and the exposure frequency. So here, the exposure frequency is just our previous example, our original example in distribution px, which represents the probability of the scenario happen in the real world. And then the maneuver challenging is given the scenario, what is the probability of the crash in a surrogate model of the CAVs. So then the surrogate, what is the surrogate model? The surrogate model is a replacement of the real ADS with some common features or generic features. For example, if whether the follow a leading vehicle with a proper distance, or interact or react to the maneuvers of the surrounding vehicles. That's the common features of the driving model. And why do we need a surrogate model? First, it provides the domain knowledge for the maneuver challenge evaluation as defined in the criticality definition. And second is that because most of the time the ADS is the exact ADS model is unavailable. Assume that if we are a third-party test facility, there are some weak OEMs come to our test facility to conduct tests, and it is highly unlikely that they will provide us exactly the ADS model for the testing. So that's why we need a surrogate model to evaluate the performance. And then how do we construct a surrogate model? First, if we have a simplified or high-level ADS model, for example, a high-level path planning model, we can use this model as our as a surrogate model. And this is exactly what we used in our case studies, because we know what is the path planning model of our Mcity vehicle. And if the high-level ADS model is unavailable, we can also use a calibrated human driving model to serve as a surrogate model, because the human drivers are natural baseline for the ADS models. Okay, so then the testing scenario library generation process can be summarized as how to identify a set of critical scenarios that can accurately and efficiently evaluate the safety performance. Right. So let's say if this is the entire scenario space, big X, and if we can find a small set with their criticality value of V is greater than the threshold gamma, then by identifying this new small set and calculate their criticality value, this is our scenario library phi. Okay, so now the question becomes, how do we calculate or how do we estimate the criticality values of each scenario in the scenario space? So before answering that question, we assume now we assume if we already have this Vx, and I will introduce or Shuo will introduce how do we calculate this Vx. If we now if we now assume that Vx is already available, then we can propose our new sampling distributions or the importance functions. So we propose two sampling policies. One is greedy sampling policy, which means we only sample the scenarios within the library based on their criticality values. And then the next one is epsilon greedy sampling policy. That means we, with some probability, we sample within the scenario library. And with some other probability, we sample outside the library within the scenario space. Okay. So, if we recall these two research questions we want to answer is that first, whether this new sampling policy or the importance function is accurate or unbiased, and second, whether it improves the efficiency. Right. So we proposed and proved some theorems regarding these two characteristics. So I will not go into details of the proof. If you are interested, you can take a look at our new paper. But the basic idea is the theorem one says that the greedy sampling policy is unbiased under some conditions. The condition is when all the contributing scenarios to the performance index are included in the library. And that is actually a pretty strong condition. But however, the epsilon greedy sampling policy is always unbiased. So that is actually a better choice. And the second theorem says under some very strict conditions, for example, on the greedy sampling policy, when all the contributing scenarios are within the library, and also the performance of the surrogate model and the testing ADS are the same, then the estimation variance can be 0. That is a very strict condition that most of the time it cannot fulfill. But this theorem actually provides some insights of where is the source of the variance. That is the dissimilarity between the surrogate model and the ADS model. Right. And then the next corollary says that if we can choose a good epsilon, which is the hyperparameter in the epsilon greedy sampling policy, if we can choose a good epsilon, then we can kind of minimize the estimation variance within the library. And also because most of the contributing scenarios are included within the library, as a result, the epsilon should be chose to a value close to 0. So that means that for most of the time, with a very high probability, we should exploit within the library, and with a smaller probability, we need to explore outside the library. And finally, this corollary 2 provides some guidance of how to choose another hyperparameter gamma, which is the threshold for choosing the critical scenarios. And it also gives an upper bound of the estimation variance. So now we analyzed the different characteristics in terms of the efficiency and accuracy of our proposed new sampling policy. And also we have 2 corollaries to give guidance of how to choose these 2 important hyperparameters. Now we present the overview of the entire framework. So we start from the scenario description, which is basically to define the ODD of the testing scenario, with what category we want to test and what are the environmental parameters. After this is determined, then we design our metrics. Here, actually, in our case, we currently use the crash rate to evaluate the safety. And then we go to this library generation process, and we generate the scenario library based on our critical definition, and also the analysis of the maneuver challenge from surrogate model and the exposure frequency from the naturalistic driving data. And with the generated library, we do the sampling, right? The new sampling policy. And then we plug the sampled scenarios into the augmented reality test environment and test with the real AADS. And finally, we output the testing results and to estimate the performance index. So this is the entire framework. Okay, so so far I have not. So far there's still a remaining question I have not introduced. That is how to calculate the criticality of each scenario. So because we adopted different methods to calculate the criticality value in different case studies. So next, the Shuo will introduce the case studies and how do we calculate the criticality values.
Okay, next I will introduce the case studies of this project, including a cut-in case and a cut-in case. The cut-in case is a low-dimension scenario, and the cut-in case is a high-dimension scenario. We will introduce more details of the dimensionality later. So the next slide. In this project, we will utilize the naturalistic driving database at UMTRI, including the IVBSS database and the safety pilot database. The IVBSS database has 16 vehicles, each with a prototype crash warning system with radar and cameras. And the safety pilot database has over 2,800 personal vehicles, trunk fleets, and transit buses. About 140 vehicles are equipped with mobile eye and data acquisition system, and we collected about 35 million miles or 1.2 million hours of driving. And the next slide, I will introduce the cut-in case study. Cut-in is one of the most common scenarios in naturalistic driving environment. We utilize the crash rate as the safety performance of the ADS to simplify the problem and to make it easier for visualization. We only consider the decision variables as the cut-in moment. That means that the decision variable X is composed of the 2 dimensions, the range and the range rate as the cut-in moment. Here, the range denotes the relative speeds of the background vehicles and the ADS at the cutting moment, and the range rate denotes the relative speed between the two vehicles. So by analyzing the NDD from Safety Pilot database, we queried about more than 400,000 lane changing maneuvers from the database. So the left figure denotes the locations of all lane changing maneuvers. For each maneuver, lane changing maneuvers, we will identify the cutting moment and recall the range and the range rate at the cutting moment. So then, by analyzing all the data, we can calculate the exposure frequency of all the cutting scenarios. As shown in the right figure, each point denotes one specific cutting scenario. Here, the x-axis denotes the range rate at the cutting moment, and the y-axis denotes the range at the cutting moment. The color here denotes the exposure frequency of each cutting scenario. The next slide, okay, we will construct a surrogate model to estimate the maneuver challenge of the ADS. Here, since we will evaluate the Lincoln MKZ at Mcity, we utilize the high-level planning model adapted by the MKZ vehicle and the test. Specifically, we will utilize the GIPS conforming model, and the value of parameters and constraints are also obtained from the ADS vehicle. So, searching for the critical scenarios of the low-dimensional scenarios, we will design an auxiliary objective function which can help us provide searching directions for critical scenarios. Basically, the objective function, capital G, is composed of two terms. The first term is an estimation of maneuver challenge, and the second term is an estimation of the exposure frequency, which is consistent with the criticality definition we discussed before. So the maneuver challenge is estimated by, we call the minimal normalized positive enhanced time to collision. Basically, it's an extension of the time to collision to help us to identify the most challenging situation of the scenario during simulation. And the exposure frequency is measured by the distance between the scenario X to a common set, omega. Here, omega denotes the region where the scenario have higher exposure frequency in the natural driving environment, which can predetermined by NDD analysis process. So the critical scenario searching method here is illustrated in this framework. Basically, we construct the auxiliary objective function based on the criticality definition, and then we solve the optimization problem based on multi-state optimization method. So by the optimization method, we can obtain several local critical scenarios, and then we searching the neighborhood of the local critical scenarios by state-figging method. Finally, we can obtain the whole set of the critical scenarios. As shown in the bottom figure. So the right figure denotes the set of all critical scenarios. Here, each red dot denotes one specific critical scenario, and all red dots denotes the whole set of critical scenarios, which can construct the library. And the left figure denotes their criticality values. So since we have determined the threshold gamma as we discussed before, then here the critical scenario are identified which the criticality values are larger than the predetermined threshold. Finally, we can obtain the critical scenario library. So the left top figure denotes the exposure frequency, which we calculated from the NDD, and the left bottom figure denotes the maneuver challenge, which we obtained by simulating the surrogate model. So based on the critical scenario searching method, we can identify all the critical scenarios as illustrated in the right figure. So here, the color denotes the normalized criticality value of each scenario, which also the sampling probability of each scenario when we're testing the ADS. Okay, here is the video of our field test execution. So basically, the left top denotes the scenario in the point of ADS view. So you can see that simulated background vehicle will cut in from the ADS, and the ADS will respond to the simulated background vehicle. The left bottom figure denotes the range and the range rate between the two vehicles. So it is an example of the near crash situation. So as you can see that the range, the blue line, almost zero in the worst case, and then okay, so that's the near crash situation. And the third one is a crash testing scenario. So the background vehicle will cut in with a smaller range and range rate, so that it's very dangerous for the ADS. So then you can see the minimal range is smaller than 0, which means a crash. Okay, so after testing several times of the ADS in our augmented reality testing platform, we can show that we can obtain the estimation result of the ADS performance. The left figure denotes the estimation of the accident rate. So here, the x-axis denotes number of tests for the NDD evaluation method, which means that if we're testing the ADS with the scenario sampling directly from the NDD, and the top axis denotes the number of tests for the proposed method. So as you can see, both methods can obtain the same accurate accident rate, but the proposed method just use a much smaller number of tests. So the right figure denotes the relative half width. As we talked before, the relative half width can provide a measure of the estimation accuracy. So as you can see, if you want to reach a predetermined accuracy, here is a 0.2, then the proposed method can obtain the same accuracy with a much smaller number of times. So the conclusion here is that we can obtain the same accurate estimation with about 100,000 times faster than the unrolled test method. Next, I will introduce you the carfogging case study. So carfogging is also one of the most common scenarios in naturalistic driving environment. We also use the crash rate as the safety performance of the ADS. But differently, the carfogging case is a high-dimensional scenario. So here we formulated the single variable x. You can see the x is composed of several terms. The first term is the initial speed of the background vehicle. The second is the initial range between the two vehicles. The third is the initial range rate between the two vehicles. And after that, there are mu ui denotes the acceleration of the background vehicle as the time step I. So if the carfogging scenario lasts for 30 seconds and the background vehicle is controlled at each 1 second, then the dimension of the decision variable x will be 33, which is much higher than the cut-in scenario. So next slide. Okay, so since the scenario is much higher than the optimization-based critical scenario search method is cannot be directly applied. To solve the cost of dimensionality problem here, we proposed a new method based on the Markov decision process. So you can see the bottom figure, which can illustrate our basic idea. Here we use a circle denotes the state of the scenario. For the carfogging scenario, the state can be the speed of the background vehicle, the range and the range rate between two vehicles, and we use the arrow denotes the action of the background vehicles. Here is for the carfogging case, it is the acceleration of the background vehicle. So each branch of state and actions can denote a specific scenario, and all the decision tree can denote the scenario space. So if we can somehow identify all the critical branches denoted by the red circle and the red arrows, then we can obtain the critical scenarios by the pruned decision tree. So to achieve this idea, basically, first we will formulate the scenario as a Markov decision process, and then we define the state action pair Q by the following equation. So theoretically, we can prove that by this definition, the Q is consistent to the scenario criticality, which we defined before. We will not introduce the theoretical details here, but you can look at the more details in our paper. Okay. The next slide, I will to obtain the Q values, we will utilize the temporal difference reinforcement learning method. So basically, you can see the bottom two figures. The left one denotes the training process. After about 20 minutes, we can obtain the accurate the values of the Q functions. And the right one denotes the probability of actions at state S. So here, x-axis denotes the acceleration of the background vehicles, and the y-axis denotes the probability, sampling probability of the acceleration at that state. So the state here is the 38 velocity of the background vehicle, and 6 range between two background vehicle, and -2 range rate between two background vehicle. So as you can see that, as denoted by the blue line, the probability of acceleration of the background vehicle in naturalistic driving environment, most time is around 0. Which is intuitive, because most times the background vehicle will have no acceleration or deceleration. But it is not challenged for the ADS performance evaluation. So in our method, the red line denotes the new probability of the acceleration of the background vehicle. As you can see that the new distribution will be more challenging and more critical. So by sampling from this distribution, we test the adaptive close control plus autonomous emergency braking at our testing ADS. And similarly, we can also obtain the two figures. The left one denotes the estimation of the accident rate. Similarly, the bottom axis denotes the number of tests for the NDD evaluation, and the top axis denotes the number of tests for the proposed method. So as you can see, both the method can obtain the same accurate estimation of the accident rate, and also we can also for a predetermined estimation accuracy, the proposed method can obtain the accuracy with a much smaller number of tests. So basically, we can obtain the same accurate estimation with 30,000 times faster than the on-road test. So now we draw our conclusions and discuss the future research. First, we developed an augmented reality testing environment to introduce background traffic into closed test facilities to facilitate ADS testing and evaluation. Then we developed methodologies to identify critical testing scenarios that can accurately and efficiently assess the safety performance. And finally, we implemented the assessment framework at Mcity Test Facility with a level 4 ADS. In future, first, we will develop an adaptive testing method, which means that after we obtain some testing result of the ADS, we can further customize and optimize the testing scenario library generation based on the existing testing result. And second, we want to develop a method for the real world driving scenarios, for example, the highway driving scenario, which including car fogging, lane changing, merging, and something like that. That's a much more complex scenario. We need to extend our methodology. Okay, so finally, thanks for the CCAT and Mcity for supporting our project.